we're going to start talking in biochemistry about the lipids. But before we talk about the lipids, I want to talk about the fatty acids, which are a part of many lipids. So as you can see, we have 6 classes of lipids, and none of these classes are fatty acids. Fatty acids are a part of the lipids, but they are not themselves lipids. So you'll notice that in the first 4, we do have fatty acids as part of the compound. So let's look at what fatty acids are and how we can classify those. Fatty acids are defined as carboxylic acids that have long hydrocarbon chains. Up to this point, we've learned how to name up to 10 carbons long. In the case of the fatty acids, they'll have more than 12 carbons, generally between 12 and 24 carbons long total. Now notice that these will always have one carboxylic acid group. That makes them part of the fatty acid. That's the acid part of its name. And then it will have between 12 and 24 carbons total, and those will always be an even number of carbons. But notice that when we're counting them, sometimes we count that C double bond OO, the carboxyl group, separately, so the rest of the carbons will have an odd number. Next, we know that these hydrocarbon chains are straight rather than branched. That doesn't mean that they don't wiggle back and forth. That just means that they don't have any branches. And finally, the hydrocarbon chains may have double bonds in them. They won't have triple bonds, but they may have double bonds in them. And we have a different name for them when they do. We call that unsaturated when it has a double bond. Otherwise, if it's all single bonds, it's saturated fatty acid. Notice that in this case, I am drawing each one with a distinctive point. But as we continue on, I'm going to just say it's a fatty acid. I don't know how many carbons it is. It doesn't matter for many of the things that we're doing. So I'm just going to often draw it as just a squiggle, showing that there's a long hydrocarbon tail. You've probably heard of saturated fats and unsaturated fats, and we're going to look at that a little bit. We're going to look at monounsaturated and polyunsaturated and saturated fats to see what is the difference between them. Now, you probably heard about them because of their dietary effects. We're going to talk about that a little bit later. But we want to first figure out what is a saturated fat, a monounsaturated fat, and a polyunsaturated fat. And that is going to be related to the fatty acids that are present. So a saturated fat will have a saturated fatty acid, a monounsaturated fat will have monounsaturated fatty acids, and a polyunsaturated fat will have polyunsaturated fatty acids. So what does that mean? When we look at a saturated fat, that tells us that it is completely saturated, which means that it has all the hydrogens that are possible attached to all of those carbons. There are no double bonds or triple bonds. When we look at a monounsaturated fat, it tells us that there is one double bond somewhere, so we're missing 2 hydrogens. And next we look at a polyunsaturated fat, and there are many of those. In those cases, we have more than one double bond somewhere in the fatty acid. Recall that in organic chemistry, we were able to write a general formula for something that told us the ratio of carbons and hydrogens, and in this case, oxygens. We can do the same thing for a saturated fatty acid, and that formula is CnH2n plus 1 COOH. And I want to show you why that is. If you recall, the formula for a saturated hydrocarbon was CnH2n plus 2. Now we're going to have plus 1 instead. And so when we look at this, we're actually going to chop off that carboxyl group, and we're going to count the number of carbons on the other side of it, and then we're going to add that carboxyl group in at the end of the formula. And because we're adding it at the end, it's taking the place of a hydrogen. If this had just been a long hydrocarbon chain, then you would see that we added at the end the COOH, so we're taking away one hydrogen and putting that COOH in that place. So for example, here we have stearic acid. It has a total of 18 carbons. We're going to chop off that last one, the COOH, and we're going to count the other carbons and find out how many hydrogens there are. So if you look at it, every carbon has 2 hydrogens, except for the very first one. Notice that it has an extra hydrogen. So that's where we get the CN, in this case 17, H2N, because there's 2 hydrogens for every carbon, plus 1, and that's because of the one on the end. And then the rest of the formula is the COOH that we see for the carboxylic acid. So in this formula, we will have C17, H2 times 17 plus 1, so that is 34 plus 1, which is 35, COOH. And that is our formula for stearic acid. In the monounsaturated fatty acids, we remove one pair of hydrogens, one from each carbon. And so we're putting in a double bond and we're removing two hydrogens to make that double bond. In the formula, we're not going to do a general formula for this, but we're just going to look at how that compares. So if I were to look at this one, I will have 17 carbons plus the COOH at the end, and now instead of 35 hydrogens, I'll only have 33 hydrogens. If we look at the polyunsaturated fatty acids, I've made all of these with 18 carbons. We have linoleic acid. This one has 2 double bonds, so I'm removing 4 hydrogens. I've gone down to now 31 hydrogens total, so it'll be C17H31COOH. And our last one, linolenic acid, which has 3 double bonds, so again we're going to be taking away 6 hydrogens in this case, and we get C17H29COOH. Let's look a little bit more at how we can tell if a compound is saturated or unsaturated by looking at the number of hydrogens and using that general formula. To decide if something is saturated or unsaturated fatty acid, you will need to know how many double bonds are present. A saturated fatty acid will have no double bonds, a monounsaturated fatty acid will have 1 double bond, and polyunsaturated fatty acids have more than 1 double bond. We're going to be calling this the degrees of unsaturation. So if there are 0 double bonds, we will say it has 0 degrees of unsaturation. 1 would be 1 degree, and 2 double bonds would be 2 degrees of unsaturation. This is also going to help us to determine how many double bonds there are. We're going to be using the general formula for a saturated fatty acid, comparing the compound that we're looking at to that formula to decide how many double bonds there are. So recall that the general formula for the saturated fatty acid is CnH2n plus 1 COOH. On these problems, N will always be given to you as the number of carbons in the long hydrocarbon chain. Your job will be to find out how many hydrogens it should have, and then you're going to compare that to the number of hydrogens that it actually has, which will be given in the question. So let's start by finding out what the formula is for a variety of saturated fatty acids. Then we'll use that number to find out how many degrees of unsaturation we have in different compounds. Let's start by looking at a fatty acid that has 12 carbons in it. We're going to take 1 out for the COOH. We're going to leave the other part of it as CN, which will be 11. In this case, our number of carbons will be 11. Even though we had 12 to start with, we pulled 1 out for the carboxyl group. Now, how many hydrogens should we have for that? And to calculate that, we're going to take 2 times the number of carbons, so 2 times 11 plus 1. 2 times 11 is 22, plus 1 is 23. Our formula would be CnH23COOH. That will be for the saturated fatty acid that has 12 carbons. Now it's your turn to try it. Let's try it with something that has C22, a total of 22 carbons. And I want you to pause the video, try the problem, and then when you come back, I'll give you the answer. We have 22 carbons total. We take 1 out for the COOH. That leaves us 21 carbons in the formula. So C21, H 2 times 21, which is 42, plus 1, which is 43, COOH is the formula for a C22 saturated fatty acid. I'm going to have you try 2 more, and then pause the video and restart it once you've done the calculation. So let's do one with 16 carbons and one with 20 carbons. Go ahead and pause the video now. Okay, let's start with the one with 16 carbons total. We're going to take 1 out for the C double bond OH, and we're going to leave the other part. We're going to have C15. Then we're going to see H 2 times 15, which is 30, plus 1. Our formula will be C15H31COOH. That will be a saturated fatty acid that has 16 carbons. And now let's look at the one with 20 carbons total. That means that there are 19 in the main portion of the fatty acid, and then our formula will be CnH 2 times 19, which is 38, plus 1 is 39, COOH. So our formula is C19H39COOH. So those are all expected amounts of hydrogens for saturated fatty acids. There are a few things to note about this. First off, notice that the number of carbons total is always an even number. That's what we expect for fatty acids, always an even number of carbons. And then in our formula that we only have an odd number in the formula for the first part, the CN part, because we've pulled out the COOH. What we're going to do next is I'm going to give you some different formulas and then ask you to characterize them as saturated fatty acids or unsaturated fatty acids. Then we'll use those number of hydrogens to calculate how many double bonds there are, and we'll decide if something is a saturated fatty acid, a monounsaturated fatty acid, or a polyunsaturated fatty acid. So here are some samples. We have 6 samples. I'm going to do the first 2 with you, then I'll leave the rest of them for you to try, and of course I'll show you after you've tried them. So let's look at the first one. We have C21H43COOH. Is this saturated or unsaturated? Well, in order to determine that, we need to look at what it should be if it were saturated. And according to our formula, C21H43COOH, we see over here, is our saturated formula. So this one's saturated. Our degrees of unsaturation is 0. We have 0 unsaturation and 0 double bonds. Let's try the next one. We see C21H39COOH. Here we see that we are short a few hydrogens. With 21 carbons, we should have 43, but we do not have 43 hydrogens. We only have 39. That means that this is an unsaturated compound. Now we can calculate the degrees of unsaturation. For this, what we need to do is compare the number of hydrogens we should have to the numbers that we actually have. So in our formula, a saturated fatty acid with 22 carbons is C21H43COOH. We only have C21H39COOH. If we look at the difference in the number of hydrogens, we see that that is 4 hydrogens difference. Remember, every double bond will use 2 hydrogens. That means we have 2 degrees of unsaturation, or 2 double bonds. That means that this is a polyunsaturated fatty acid. Now you try C21H25COOH. Decide if it's saturated or unsaturated, and the degree of unsaturation if it is unsaturated. Go ahead and pause the video and restart it again, and then we'll have you do the last 3. Okay, so let's see if it's saturated or unsaturated first. We're going to compare our number of carbons. We see that we have C21. If it were saturated, it should have 43 hydrogens. In this case, we only have 25, and so we know that this must be an unsaturated fatty acid. Now let's find out what the degree of unsaturation is. So all you're going to do is you're going to take 43 minus 25, which is the difference in the number of hydrogens, which is a difference of 18 hydrogens. Remembering that every double bond uses 2 hydrogens, we see that there must be 9 double bonds, and this is definitely a polyunsaturated fatty acid. So now go ahead and pause the video and restart it once you've done the last 3 of them, and I'll go over all of those at the same time. Okay, let's start with C15H25COOH. Here we're going to compare that to our C16 carbon, which has a total of 16 carbons, and that tells us that if it's saturated, it should have C15H31COOH, and we only have 25 hydrogens, C15H25COOH, and so that means there is a difference of 6, and so that means that there are 3 double bonds. Our degrees of unsaturation is 3. Now let's try C19H37COOH. And here we see if we have a total of 20 carbons, or 19 in the long hydrocarbon tail, we see that it should be, if it were saturated, C19H39COOH. And here we only have 37 hydrogens. That's a difference of 2 hydrogens, which means we have 1 double bond, 1 degree of unsaturation, and that means that we have a monounsaturated fatty acid. And now our last one, we have C23H41COOH. In this case, we have not done the calculation to find out what it would be saturated, but let's go ahead and do it. If I have a 23 here, a total of 24 carbons, but only 23 in the hydrocarbon tail, we're going to put C23H 2 times 23, which is 46, plus 1, so H47 is what we should have for our formula, COOH. In this case, we only have H41, so C23H41 COOH. The difference between these two formulas is a difference of 6, which is 3 degrees of unsaturation or 3 double bonds, making this a polyunsaturated fatty acid. Now let's look at how the degree of unsaturation affects the melting point. So here we're going to compare how many double bonds there are to what the melting point is. For example, we're going to look at the saturated fatty acid that we have here, stearic acid. It has no double bonds, degree of unsaturation is 0, the melting point is 69 degrees Celsius. We go to a monounsaturated fatty acid, we put in 1 double bond, and it becomes 14 degrees Celsius. You can see that the melting point has dropped dramatically by putting in 1 double bond. When we go to the polyunsaturated fatty acids, we put in 2 double bonds, it goes down to -5 degrees Celsius, and linolenic acid, which 3 double bonds, goes down to -11 degrees Celsius. So hopefully you can see the trend that as we increase the number of double bonds, the boiling point and melting point decrease. So there's an inverse relationship, more double bonds, lower melting point. We can also look at this at the number of hydrogens. So in this case, I made all of these with C17, but I've changed the number of hydrogens that are present. So stearic acid had C17H35 COOH. Oleic acid has C17H33 COOH. Linoleic acid has C17H31 COOH, and linolenic acid has C17H29 COOH. And so as we change the number of hydrogens, we can see the number of hydrogens is decreasing given the same number of carbons. That is the same direction as the melting point. So we have some relationships we can make out of this. The melting point of the fatty acids decrease with increasing degree of unsaturation. You could also say the melting point of the fatty acids decreases with increasing number of carbon double bonds. Or you could say that the melting point of the fatty acids decreases with a decrease in the number of hydrogens. So let's see how we can apply that. We want to find out which of the following has the highest melting point and which one has the lowest melting point. So we're going to start by figuring out how many double bonds each of them has. Notice that in this comparison, we always have to have the same number of carbons to make the comparison. If you change the number of carbons, you're going to change the melting point, and that will not be determined by this. So here we all have C21. They all have COOH. The only thing that is different is the number of hydrogens. The first one is a saturated one. If you go back to our formula, CN, N is 21, H 21 times 2, which is 42, plus 1 is 43. We see that this is a saturated fatty acid, has 0 double bonds, and that should have your highest melting point. Then we look at C21H39 COOH and C21H25 COOH. The saturated form should have 43 hydrogens. The second one has fewer hydrogens, and the third one has even less hydrogens. Without doing any calculations at all to find out how many there are, we see that the one with the least amount of hydrogens should have the lowest melting point. So that'll be our C21H25 COOH. For the following 3 sets of compounds, I'd like you to try it. See if you can identify which has the highest melting point, which one has the lowest melting point, and in the third case, see if you can rank them from lowest melting point to highest melting point. Go ahead and pause the video, and then when you've got it completed, restart it. For the first set, we see that they are both C15, so all we need to do is compare the number of hydrogens. You can readily tell that C15H29 has more hydrogens than C15H23 COOH, and so the top one is the higher melting point and the bottom one is the lower melting point. We could do the same thing with the second set. We both have 13 carbons. The only difference is the number of hydrogens. In this case, the second one has more hydrogens, so it has a higher melting point, and the first one has fewer hydrogens, so it has a lower melting point. And on the bottom, we can see how we can rank all of them. So we've got 4 of them, all with C17. And what we should look for is the one with the most hydrogens should have the highest melting point. And that is the third one in this list. So we see C17H33, COOH. That'll be our highest melting. And our lowest melting point will be found with the one with the fewest hydrogens. And that is the bottom one, C17H15, COOH. And that means we have to figure out the other 2 in between. And so if we're ranking them from lowest to highest, the bottom one is your lowest and the top one is your highest. We just need to figure out the other ones. So we're going to go from lowest. We're going to say what is the one with the next most number of hydrogens, and that'll be the one with C17H23, COOH. So our second one on the list is going to be our second lowest melting, and the next one will be C17H27, COOH, with our highest melting being C17H33, COOH. I'm going to put a little A, B, C, and D between them so that you can see how they would look on a quiz. If I were to rank these from lowest to highest, we would see the lowest one is D, the next one is B, the next highest one is letter A, and our highest melting point one is letter C. At this point, you might be asking yourself, why do we even care about the melting points of fatty acids? Well, we may also ask, why do we care if we have saturated or unsaturated fats in our diets? And does it matter if it's monounsaturated or polyunsaturated? What is the difference? Which one's the healthy one? So we're going to use those melting points to answer the question about whether a fat is a healthy fat or a unhealthy fat. And to answer that, we need to know, why do we worry about fats in our diet at all? The major medical concern with fats is heart attacks. Heart attacks come from a blocked artery being blocked by all of those fats collecting on the inside. As fats begin to collect on the inside of the artery, we will start to see the pressure build, and we get an increase in blood pressure, which is why doctors always check your blood pressure to see if you're starting to get some clogging at that point. Then, over time, as the hole gets smaller and smaller, the blood pressure increases, but at some point it completely stops. Once the flow of blood is stopped, your body has a heart attack. And why do those fats start to collect and clog the artery? Well, the main reason is sort of like when you watch a leaf going down in the gutter. You'll see that they collect whenever there's a small point. It's going to continue to collect on that spot. So it flows nice and smooth until it hits some little rough spot. When it hits that spot, more and more of those leaves start to collect, and that's similar to the way that the fats flowing in the artery will continue to flow until they hit something. Once they hit that something, they start to collect at that point. But you may notice that at that same point, the liquid continues to go by. It's the solid that gets caught. So the reason that we care about the melting point of the fatty acids is that we care about the fact that the fatty acid and its fat that it's going to be related to are either going to be solids or liquids. The more liquid-like, the more that will flow past. But as the fats become more solid, they start to clog the arteries. So these are the melting points of the fatty acids we looked at earlier. And that means that these are the temperatures at which these compounds turn from a solid to a liquid. So we see stearic acid melts at 69 degrees, oleic acid melts at 14 degrees Celsius, and so on. And I'm going to put some regular temperatures in here to give you some context as to what these temperatures mean. So you already know that water melts at 0 degrees Celsius. And now we're just adding in 2 other temperatures that are commonly used. We have room temperature around 20 degrees Celsius, 20, 22, somewhere in that region. And we have body temperature around 37 degrees Celsius. Now the reason these are important is because that's what we see in everyday life. So now let's look at what state we expect stearic acid to be
at room temperature or body temperature. We should see that since it's 69 degrees Celsius it melts, that's well above body temperature. Stearic acid should be a solid within the body and at room temperature. On the other hand, when we get to oleic acid with just one double bond, the melting point has dropped so that now oleic acid is a liquid at room temperature and body temperature. So you can see that having one double bond causes the same number of carbons to be a liquid rather than a solid. So this helps us to stop clogging of arteries as soon as you put in double bonds. And notice that the more double bonds you put in, the lower it is. And so we'll have more likely to have a liquid in the body which will pass through the arteries rather than clogging them. Now note that these are just the fatty acids themselves, not the fats that we find in our body, which have 2 or 3 of these joined together. And so we see that these differences in melting point will be shifted by various amounts. Now some fats have one chain of one of the fatty acids and one of another, so we might have mixtures of these, but we can see that the more double bonds there are, definitely the lower the melting point will be, and the more likely the substance is to be a liquid and less harmful to the body. What we know is that the polyunsaturated fats are the healthiest, monounsaturated is okay, and that the saturated fats are the least healthy because they are the most likely to clog your arteries. And again, it's going to follow the same pattern that we see for these fatty acids. So here we have our saturated fatty acid, the stearic acid, our monounsaturated fatty acid, oleic acid, and our polyunsaturated fatty acid, linoleic acid. And what I want you to notice is their shapes. So notice that oleic acid and linoleic acid both have double bonds in them. Those are cis double bonds, so that means that they go to the same direction. And we can see that the structure bends a little bit when we put those cis double bonds in. When we find that something is a solid, a liquid, or a gas, we're looking at the interparticular forces that hold them together. Specifically, we're going to be looking at London forces because these are fairly non-polar substances because of the long hydrocarbon tail that we see on each of them. So what I'm going to do is I'm going to put a collection of these together and see if you can see what happens when we start to pile them on top of each other. Hopefully you can see that the stearic acid tends to align itself because its structure is very, very consistent, whereas the oleic acid has that bend in it and it makes it very hard for the particles to line up as they should, and even worse in the linoleic acid. So the less that they line up, the lower the melting point becomes. I'm going to give you a little side note about McDonald's French fries. And this is to talk about how our relationship with fats and oils has changed a business. So back in the 50s when McDonald's started out and they had their French fries, they used to use saturated fat, a beef, to deep fry their French fries. Sometime during the 80s it was discovered that the saturated fats were very unhealthy because they did clog arteries, and so McDonald's went with the times and they switched over to hydrogenated vegetable oil. Now the reason they use hydrogenated vegetable oil is because it was a monounsaturated fat. McDonald's chose to use these hydrogenated vegetable oils because they were solids at room temperature and were easier to work with, and they had higher boiling points, which means that the French fries cooked faster, and they were more shelf stable, which means that they didn't get old as fast. And so all of these things led McDonald's to choose the hydrogenated vegetable oils. Over time, sometime in the 2000s, it was discovered that these trans fats were no healthier than the saturated fats. So in 2008, McDonald's decided to change over to the polyunsaturated canola oil that it currently uses. Now this is a liquid which is less shelf stable, which means it expires faster. So McDonald's has a much higher price on their French fries now because of this canola oil switch. It is healthier for us, although you're still eating fries, but it is definitely more expensive for McDonald's because they're constantly replacing their oils. Now, one of the things that has happened is that large companies like McDonald's are able to resell the used oils
to make biodiesel. And so that's one of the big benefits of science is we've developed a new way for them to recycle and recapture some of the money they would have lost on the disposal of fat. They can now dispose of it and make biodiesel out of it so they don't lose quite as much money. So I'm going to talk just briefly about what the trans fat is and why it was a little bit different from the others. So we're going to start with a drawing of a saturated fat, and again they stack on top of each other when there's a collection of them, and that's why they're a solid. And then we have our unsaturated fats, and I'm going to go with a polyunsaturated one so that you can see what it looks like. And you can see again they don't stack on top of each other, they kind of make a mess. When we look at the hydrogenated vegetable oil, one of the things that's unusual about it is when we make a man-made double bond, instead of having the cis double bond that we would have had before, we now have a trans double bond. And we're going to look at how that affects the structure by drawing it here. And hopefully you can see how this is very similar to the saturated fat. And what happens is it does stack on top of each other very nicely as the saturated fat does. It makes a solid at room temperature, and so that is why it's as unhealthy as a saturated fat, even though it seems like it's better because it came from a vegetable source. Once we hydrogenate it, it makes it back to being unhealthy. The next video is going to talk about how the fatty acids are a part of the various different lipids, starting with the triglycerides.